So this will be a physical experiment providing physical evidence for the validity of the energy equations mgh, which is equal to half mv squared kinetic energy. The experiment will basically be dropping a 2 mass, a 3 mass and a 4 mass, all from one height, resulting in one velocity. And then we will pit that against a 1 mass dropping 2 heights, achieving 1.41 velocity, and then we will drop a 1 mass from 3 heights, achieving 1.732 velocity, and we will drop a 1 mass from 4 heights, achieving twice the velocity. MGH and kinetic energy formulas would suggest that these are the same energy. MGT, which is equal to P, would suggest something different. So we'll just quickly look at that in terms of MGH, which is very straightforward, and then kinetic energy, and then we can also look at MGT, which is equal to momentum, and what that would predict. In terms of MGH, it's pretty straightforward. They're just the inverse of each other. So if we were dropping a 1 mass from 2 heights and a 2 mass from 1 height, obviously with gravity on both sides, we don't have to bother with that. We can just use the mass and the height, and they would suggest that in all these cases they are equal. So we'll look at that in terms of kinetic energy as well, because obviously MGH is equal to kinetic energy as well. So if we look at the kinetic energy, we've got a 2 mass, 3 mass and a 4 mass, all gain 1 velocity. So with half the mass, which would be 1, square the velocity, which would be 1, so 1 times 1 is 1. 3 mass, half the mass, 1.5, times velocity squared, which would be 1, equal 1.5, and the 4 mass, half the mass, times the velocity squared, which would be 2. And then on this side, we've got 0.5, 0.5, 0.5, because we were using a 1 mass on each drop, so we half the mass. Velocity would be 1.41 squared, which would be 2. 0.5 times 2 equals 1. So you can see we've got equivalency. Half the mass again, so 0.5 times the velocity squared, which would be 1.732. Square that, we get 3. 0.5 times 3 equals 1.5. Again, equivalency. And half the mass, 0.5 times the velocity, which would be 2. 2 squared would be 4. 0.5 times 4 would equal 2. And again, we can see equivalency. So in both cases of the MGH and the kinetic energy would suggest that the energies for both these masses dropped, all these masses dropped, would be equal energy. If we were using the MGT formula, which is equal to P, obviously again we've got G on both sides, so we can just go with the time. So we'll be dropping a 2 mass, a 3 mass and a 4 mass, all be dropping one distance, so all 1 unit of time. So literally 2 times 1 is 2, 3 times 1 is 3, and 4 times 1 is 4. So that would be what the MGT would predict for those masses being dropped. But if we look at this side, we've got a little bit of difference now, because we've got a 1 mass dropping at twice the height, so the time would be 1.414, so that's not equal. We've got 2 on this side and we've got 1.4 on this side. On this one we've got 3 on this side. We've got the 1 mass, it's dropping at it will take 1.732 the time, so that gives us 1.7, so that's like almost half, and well, a little more than. And then obviously the 4 mass dropping at one height, as opposed to the one mass dropping at twice the time, and that would give us 2. So, you know, it's not equal. It's showing that this would, you know, on this one it's got twice the momentum, on this one, you know, so it's saying that these are considerably less energy when they're dropped from these heights. We'll just look at that in terms of momentum. In terms of momentum, we've got the 2, 3 and 4 mass dropping at 1 unit of velocity. So again, we get 2, 3 and 4. In the case, ignore the scribbles. In the case of the 1 mass, it's going 1.414 times the velocity, 1.732 times, and 2 times. So again, we get 1.4, 1.7 and 2, which is the same as what we got up here. So mgt is equal to P or mv. Either way, gets the wrong answer. I've done my best to verify the velocities, and obviously we're dropping from 1 height, that will give us as 1 velocity. From 2 heights, that will give us 1.414 the velocity. From 3 heights, that will give us 1.732 the velocity, and from 4 heights, that will give us 2 velocity. I've done crops of each one close to impact. I tried to crop it exactly the same so we can roughly measure it. So we'll do the 1 velocity, we'll crop that, see how long that takes, and then we can make some predictions and then see what we actually get from the crop results. From the first cropping, we get 8.2 seconds. When I'm editing the video, I can see it down to points of a second, but when basically you make the video, it just goes to the nearest second. So, but all this can be verified anyway. So we're getting 8.2 seconds for 1 velocity. So we'll make some predictions from that. From the 8.2, if we divide that by 1.414, we get 5.79 seconds. If we divide the 8.2 by 1.732, we get 4.73 seconds, and obviously half of this will be 4.1. So we'll run this one, we'll run the 2 height one and see what we get in actuality. So that's it, you've just seen the 1.414 velocity at 2 heights. We predicted 5.79, and in the software, in the editing software, I can see that it's 5.8 seconds. So I'd say that's just seeing the drop from the 3 heights, going 1.732 the velocity. We predicted the time would be 4.73 seconds, and again from the software I can see that it's 4.7 seconds, so again pretty much bang on. And then from the 4 height, which you've just seen, obviously should be going 2 velocity. We predicted obviously 8.2, half of that is 4.1, and again from the software I can see that it is 4.1 seconds. So the cropping's probably not the best, it's not exactly perfect, but you know, it's a very good indication that from the heights that these are dropped from, that they are achieving all the relevant velocities. I'll just add on here that this is the best I can do with what I've got. A frame count obviously would be more preferable, so if Dispar wanted to do the frame count on all the velocities, that'd be great, because obviously that'd be way more accurate. But from the heights alone, they determine the velocity, so I'm more than confident that, you know, they're thereabouts. As before, I'll be using these plastic spacers. This is 10.5 centimeters. So it's the right leading edge I'm using. I'll just show the measurement here as best I can. It's probably not perfect, but it's thereabouts. So as you can see, it's this leading edge that I'm measuring, because that's the bit that basically I put between the spring and the masses. And as you can see there, it's pretty much bang on. So here we have double the height, 21 centimetres, and the measurement there, again, the right leading edge, because that's the bit that goes between to determine the height. 3 times the height, 31.5 centimetres. So just showing the measurement here, hooking it on the top edge, pulling it down, and roughly we have 31.5 centimetres, so that'll be as 3 height. 4 heights, 42 centimetres. So we'll show the measurement of this one. We hook it on the top edge, pull it down, and roughly you can see that it measures 42 centimetres. So that'll be as 4 height. So just verifying the masses here. We've got 24.29. Obviously we put that to one side. We'll take the next one. That's also 24.29. We put that to one side and take the next one. That's also 24.29, all in grams this. And we take the last one, and that is 24.29. So all equal. This is the spring uncompressed measurement, 74.5 millimeters. I'll just take that out and show that it's no shock absorber. It's quite easy to compress because the weights that we're dropping onto them aren't particularly heavy. So yes, it's quite springy. We have all 4 masses on the spring now, and we're going to take a measurement of that maximum compression. So with the 4 masses on, we'll measure the compression. It's really difficult to do with one hand, so obviously I've done this carefully prior to filming it. But as you can see there, that just fits in nicely from the bottom to the top of the mass, and that's 69.9 millimeters. I've just bottomed out the spring here so we can see the maximum compression it can take. Again, very difficult to film, so I've just basically put one mass on, put a stop on, pressed it down because it's not hard to compress, to see its maximum compression, and the measurement is 17.3, so we can take that off the uncompressed length to see what the maximum compression is, and we're working well within that range. In doing the experiment this way, there's always a bit of a trade-off, because obviously we've got the standing weights. If we could do it horizontally, obviously we wouldn't have that issue, but then we'd have the huge issue of getting the velocities exactly right, which gravity is really useful for that. And obviously we can account for the standing weights. You know, we can measure that and subtract them from the results to see what the results actually reveal. From the measurements, we saw that the uncompressed spring measures 74.5 millimeters. When the 4 masses are placed on the spring, we get a compression, well, the remainder was 69.9 millimeters. So we subtract this from this, and that gives us the compression of, for the 4 masses, at 4.6 millimeters. We can divide that down by 4. So for the 1 mass, we would have a compression of 1.15 millimeters. And obviously, with it being linear, we can just calculate that. So the 1 mass would be 1.15 millimeters. For the 2 mass, it would be 2.3 millimeters. For the 3 mass, it would be 3.45 millimeters. And obviously for the 4 mass, which obviously we measured, would be 4.6 millimeters. So from that, we can factor that in, because that's the standing weights on the spring. The maximum compression, when we measured that, we had 17.3 millimeters left. So uncompressed length is 74.5 minus the 17.3, and that gives us a range of 57.2 millimeters. So anywhere from 0 to 57.2 before the spring is bottoming out. So that's as healthy range. Right, we'll just set some facts out in regards to the experiment. We're testing MGH, aren't we? So we need some mass, and we need some heights, and we need some way to collect the energy. Obviously, the masses are the things that are dropping, the height is what I'll raise them to on the rod, and the spring is what collects the energy and the measurement of that compression. It's that simple, it's repeatable, it's reliable, because gravity is. The two lines circled here will be a 0 mark. I tried to line it up perfectly with that. I was a fraction off, but each probe is obviously hitting at the same point. And then I will be measuring from that corner. Obviously it's a cylinder, but you can get me reading on that. It's just for ease of reading for me. I've just taken random ones from a series of trials. I did a lot of trials, but just picked random one of each. I've cropped it, so zoomed in and freeze frame, just so we can see the measurements a little bit clearer and make the predictions. 5, 10, 15 and around about 18. We've just seen the one mass there dropping at 2 heights, and we're roughly getting 18 millimeters of compression. We've got this weight factor to deal with, so if we take the 18 and take away the weight factor of 1.15, we've got 16.85, so that would roughly be its energy. So in the case of the 2 mass, if we were to make a prediction, we've got the 2 mass dropping at 1 height. It would be the same energy, so we've got 16.85 plus the factor of the weight compression, so 2.3 added. So we could predict roughly that it's going to compress around about 19.15 millimeters. So we'll run that one and see how close to the prediction we are. So 2 mass at 1 height, got 5, 10, 15 and 19. We predicted 19.15 and we roughly got 19, so we're 0.15 millimeter off on that prediction. 5, 10, 15, 20, I'll say 21.5 on that one. So we're just seeing the one mass dropping from 3 heights. We're getting a rough compression of 21.5 millimeters. We take off the standing weight and that gives us the energy. So we've got an energy of roughly 20.35 millimeter of compression. So again, for the 3 mass at 1 height, we can add just the energy plus the added weight, which would be 3.45. So we can predict roughly 23.8 millimeter of compression. So 3 mass at 1 height, 5, 10, 15, 24. So we're just seeing the 3 mass at 1 height, we predicted 23.8 and we're roughly getting 24. So we're 0.2 of a millimeter off on that prediction. 5, 10, 15, 25.5. So now we've just seen the one mass at 4 heights, and we're roughly getting 25.5 mil of compression. We take off the 1.15, and that gives us the energy of the compression, roughly 24.35 millimeters. So again, when we drop the full mass at 1 height, this would be the energy plus the added 4.6 millimeters of weight compression. So we can roughly predict that the full mass at 1 height will compress roughly 28.95 millimeters. And the full mass at 1 height, 5, 10, 15, 20, 25, 29. And as we can see there, we roughly got 29, so we had 28.95, which is pretty close to 29. In conclusion, we can see that the kinetic energy formula and the MGH formula, the energy equations, perfectly or almost perfectly predict the results. Momentum and MGT obviously would say something different, but yeah, there's nothing wrong with these energy formulas. They perfectly predict the results. So there you go. The footage that I showed was cropped and freeze framed just for ease of seeing the readings. At the end of this video, I will tag on 5 individual runs of each drop in its raw form, unedited. The only editing there'll be a label in the corner, bottom right hand corner, just showing, telling you which drop it is, which mass and height it is. Apart from that labeling, there's absolutely no editing. So it's there to be looked at, scrutinised, for anybody who wants to, really.